Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
In this session, we have three more of Butler's friends. First is Bob Metcalfe. Bob?
Thank you all. I'm from University of Texas, and where Bob Taylor is one of our esteemed alums, and where Jay Strother-Moore is today. I think he still believes he invented pieces. They both did. Yeah. And I didn't even know they had been invented until today. So I'm here to, for one purpose only, which is to thank Butler Lampson for being my mentor. The odd fact is he was my mentor between 1972 and 78, which is 6.5 years of mentoring 35 years ago. I've forgotten half of what was going on then. I've made up the other half. And I realized I didn't know half of what was going on even when I was there. So I apologize in advance, and I do hope the various of you will try to correct me through a few of these remembrances. I urge you, since I'm such a fragile soul, that you be gentle. And if in doubt, Butler invented it. If I had to come up with a word for Butler, it would be fast. And I'm from New York. And he was the first guy I met who could say the word, who thinks that the word processor is a single syllable word. Processor. And our life was full of processors. So fast is going to come up a few times in my remarks. I was at MIT and Harvard, and I was working on the ARPANET at the time, which is now, today it's called the Internet. And I had built an IMP interface, a high-speed network interface, my first. It ran at 300 kilobits per second, connecting a real PDP-10 to the Internet. And so when I got ready for my PhD, I went out job hunting, and I got 9 job offers because the ARPANET was really hot then. So grad students in that space got lots of offers. One offer I did not get was to be a professor at MIT. And Barbara Liskov, who's here, got that job. And I think that MIT decision was vindicated by her having received the Turing Award. But I had 9 other offers, one of which was from Xerox, which paid more than the MIT offer and had no teaching responsibilities and was in California. So I prepared to skulk off to Palo Alto. And so my wife quit her job and got a new one at Stanford, and we got a house in Palo Alto on Churchill Street, and I got ready to go, and I went to my thesis defense 3 weeks. Oh, my parents arranged to come to Harvard Yard to see their son get his PhD, and I went to my thesis defense, and I failed. I don't know if any of you have ever had that experience, but it's still with me 35 years later. And so I picked up the phone and I called Xerox Parc to notify them of this event. And I'm a little vague as to who answered. I think it was probably Bob Taylor, but I know the reason I was going was to be with Butler and Chuck and Alan and Bob Taylor and Jerry Elkind and others. But somebody said the following words. They said, "Oh, don't worry, just come out here and you can finish your PhD while you're here." That was the biggest relief I've experienced in my entire life. And thank you, Butler, if you had anything to do with that. I appreciate it. Since I was a PDP-10 hacker and had been for a long time, but by then, 6 years, and I'd built some hardware, I think I was a natural to be scooped up as the plumber for Xerox CSL to put the Internet into Parc. But my first assignment was not that. Butler showed up with some sketches of the inner loops of microcode for the implementation of floating point instructions on the PDP-10 clone we were building called Max. And Butler decided that I was the perfect guy to implement the floating point instructions for the PDP-10 since I was a PDP-10 hacker. He didn't know I was an integer hacker. So Butler presents you with the metacode for the inner loop and says, finish it, which I proceeded to do, and sort of. And the constraint was that there were diagnostics that ran on the actual PDP-10 to test everything, including floating point, and my goal was to pass the PDP-10 diagnostics, which I could not do. And have I mentioned how important fast is? I was not finishing fast. And I forget a little bit about what happened, but Ed Fiala took over and he finished the job. But what we discovered was, the reason we couldn't pass the diagnostics is that the PDP-10 had a bug in its floating point instructions. And I believe it was Butler who insisted that we put the same bug into our microcode so that we could run the DEC diagnostics. And I think so then the beginning of legacy. Then I was given the job of putting Max on the ARPANET, internet, and I started work on that. That involved building another one of these cards. They were MSI cards about this big, and to connect the aforementioned data general machine to the IMP, the packet switch that we had from ARPA. And that part went pretty well because I'd done it before. But then I had to do the software to hook the Data General 800 to Max itself, to the 10X operating system that was running there. And fast wasn't happening. I was having a hell of a time get it to work. And one day, and this is where I mentioned my good friend Chuck, this is when I first realized that Chuck Thacker didn't like me. Because I couldn't get this code to work. And one day I'm typing into DDT, and I type a number into DDT, hit return, which puts the value into storage. And then I went the same number slash, which takes the value out of storage. And what came out was different from what I had just typed in. So I began to suspect that there was a bug in Max. So I told whoever was building Max, I don't want to name names, that there appeared to be a bug in Max, whereupon they came down and ran the memory diagnostic. And the memory diagnostic just flawlessly ran. And the implication was there was some sort of bug in my software that the Max clearly worked perfectly, but it was me who was slowly screwing up. So then and this is where I retaliated against whoever those people were, I wrote a virtual memory diagnostic, a diagnostic that ran in virtual memory, would put patterns down and then check them against. And then there was an ASCII character called Control G, which is the bell. So if a difference was ever detected, my code would ring the bell and type out the difference. I went to 10X, typed Munger. That was the name of it, M-U-N-G-E-R, Munger. And the program ran for about a quarter of a second when the bell started ringing. There were virtual memory bugs. So I went off to Chuck, I don't want to name names, and said, there's a problem in virtual memory. And Chuck said, you've got a bug in Munger. So after a while, we figured out that Munger didn't have a bug. And it turns out that memory had more than one port. There was the port to the processor where the diagnostic ran. And then there was the port to the disk where the pages were going in and out. And that port had bugs in it. And it wasn't my fault after all. It's been a long time coming, yes.
Bob, I did say in my talk that the Max memory didn't really work.
Oh, now you tell me.
I should have said who discovered that.
Now so my next job was that there was this kid there named Charles Simoni, or Simony. And he was, and don't call him Chuck. You see, his actual name is Karoy. Charles is his nickname, but everybody who tries to call you Chuck or Charlie, and you don't put up with it. Charlie's okay, but has more syllables than Charles. In any case, Charles had been working on a local area network. So the Alto project was starting, and we needed a network for the altos, and Charles had been working on a network before I got there called Signet, Simoni's Infinitely Glorious Network. And it was basically the ARPANET times 1,000. It was 50 megabit per second packet switches in the LAN. And so he gave me that project, and he took this other project. I remember standing with him and looking at some inner loop code for this text editor that Butler had. So Butler recruited him to go do that software thing, that text editor, and I got the networking job. Thank you, Butler, for that. So I started working on the network, and what came out of that ultimately was Ethernet, which was invented by myself and David Boggs and Butler Lampson and Chuck Thacker, all of whom have our names on the patent. And it's a really murky time, and we could fight now who thought of all these ideas. I did not invent pieces, but we did come up with Manchester encoding, and I don't know who came up with Manchester encoding, but it was a real breakthrough in the whole invention of Ethernet.
The Max disk drives.
Was it Max disk drive?
I think so.
Yeah, it was an old technology at the time.
Well, it had a name, Manchester encoding. So we chose it, and the beauty of it, it was two states. So the cable, which we decided to share the cable, instead of having a bunch of cables coming back to a big rat's nest, and we decided that this cable would be shared, and the various stations driving it would either be driving it or not, rather than 1, 0, or off, 3-state, this would be 2-state, driving it or not. And the Manchester encoding allowed it each bit. By the way, in Manchester encoding, each bit cell starts with the complement of the bit and ends with the bit. So there's a transition in the middle guaranteed. So that gives you, one, a clock. So all the attached stations put their clock in the packets. Two is it allows you to notice if a packet's going by. That's called carrier sense. And not only that, since this cable is off half the time, it allows you to detect collisions. You can see if somebody else is mucking with the cable while you are. So Manchester was a key development there. And then we chose to use thick coax to share, because there was a device that David Liddell told us about that allowed us to pierce the coax so we could install new stations without cutting the cable and bringing the network down. But then things started to slow down. We couldn't get the damn transceivers to work. That is, these transceivers had to drive this cable on or off for a mile with 255 others, and their transmissions had to be able to pass this tap without being disturbed by what's called an impedance mismatch. And we couldn't do that, and we were struggling, Dave Boggs and I, whereupon one of the two spiritual leaders of our laboratory decided that he was going to build another network, which he called XNet. This was devastating news, because here's the guy in charge of everything, our spiritual leader, expressing a lack of confidence in our ability to drive a mile of cable, and not only that, starting to accumulate resources like Larry Clark, who you just saw. Larry Clark started walking toward XNet. He's the technician who built everything, away from Ethernet over toward XNet. So I did the only reasonable thing, is I threw a tantrum. And I went into Bob Taylor's office, and he denies this. And I said, what? He was crying. You've got to stop this. And 3 days later, and I assume Chuck and Butler and Bob were all involved in this, miraculously, and Chuck's right here, so he could actually talk to this point during the Q&A period, as to who actually shut down XNet. But XNet was, within days of announcement, shut down, and the resources went back to Ethernet. We recruited a guy named Tat Lam, a consultant, who built the 4 picofarad electronic thingy at the front on the cable. You can tell how much of an electrical engineer I am. Thingy was not what they were actually called at the time. And we got it to work. And then we built an internet protocol on top of it. We started attending seminars with Vint Cerf at Stanford, and came up with a thing called TCP/IP, which our protocol was called PUP, the Parc Universal Packet. And then Butler walked into my office again, and he said, there's a printer being built called EARS. No, it wasn't called EARS yet. It needed to be called EARS. So he thought it needed Ethernet, so that instead of using SneakerNet, where you would take your 2.5 megabyte removable disk out of your Alto and you would walk over to the printer and put it in and print your documents, maybe a network would be a better way to do that. So Butler, to the extent that that was ever done, assigned me to go work with Ron Ryder to put Ethernet into this printer he was building. But then we discovered that Ron needed an operating system. And who is the king of operating systems? So he sketched a non-preemptive task switching system, which I then implemented for ears. It became the operating system for ears. And one of its tasks was to allow the task to put the packets in memory and send them off to the character generated in print. So we built ears. And ears was very important because Ethernet needed a reason. And Ethernet it turned out, had three reasons. One was everybody wanted to print on ears. So if you wanted to print on ears, you just hit, someone came up with the idea that you hit P, and then the document appears at the printer instead of this SneakerNet thing. The second reason was we implemented Telnet, which is the remote login protocol, which Butler assigned me to do. And I got it, and I'd done a Telnet before at MIT. It's not that hard. And the man who got that code when I left was Bob Sproull. You had to finish that. Oh, Ed Taft did. In any case, I started it and he finished it, but Butler gave me the job. And so we had so Telnet was the second reason for Ethernet. But then there was the third reason, and this is where Chuck comes back in. These memories, these semiconductor memories didn't work all that well. So what you wanted to do when you weren't running your machine was to run a diagnostic on memory and detect when the MOS chips were fading, roughly speaking, and if they were, report the result to some central place. And how would you report the result? Over Ethernet. So those were the three initial reasons for Ethernet. What? Well, that was later. I'm talking the Big Bang. The first microsecond of the universe. So then, just to make a long story short, Ethernet then became a DEC Intel Xerox project, which was given to the IEEE, made a standard. It's been IEEE Project Ago 2. It's been re-standardized many times for the last 40 years. And now today, about 1.2 billion new ports of Ethernet are shipped every year, if you count Wi-Fi, which I do. Then I became a pundit and then a venture capitalist for 10 years, and now I'm trying to figure out how to be a professor. But in summary, in the remaining 2 minutes and 38 seconds, Butler, I want to thank you for the things that you taught me, and I made a list of them. First, of course, is fast. In Silicon Valley, the way they say that is slow magic is not magic. So everything has to be fast, including, and you should rehearse this every morning, processor. Second, inner loops. You should do the inner loops first. Do the hard parts. Be sure the inner loops work before you do all that decoration around the inner loops. Very valuable insight. The importance of diagnostics as a check. You should be able to, I remember at Parc, and under the leadership of Butler and Chuck, there were diagnostics, like the floating point diagnostics everywhere, like the memory diagnostic that you had to be running all the time to be sure everything was working. There's a very little distinction between hardware and software. So I fit in perfectly there because I was a hardware software guy, and the distinction between hardware and firmware and software for us is important that be fluid and you not think of them as two different worlds. Another concept which I think I got from Butler, although Schroeder had something to do with it, mutual suspicion. Is that your idea?
I can't remember.
The idea of building software systems that have multiple suspicion. That is, if you're going to build a network with all this intelligence spread around, and these devices are going to deal with each other, there's two ways it could go. One is that the probability of the whole thing working is the product of the probability of all of them working, which is not good. Or by putting in mutual suspicion and redundancy, you can make it more resilient than having only a few devices. Each additional device adds redundancy, and that's accomplished through mutual suspicion. In my PhD dissertation, I referred to that as thin wire communication, but it was based on Butler's idea of mutual suspicion. The right person, putting the right person in for the right job. For example, replacing me on the floating point project with Ed Fiala was a really good move. But then I learned one other thing, which I'm going to close with. I have 15 seconds, which is you can be too fast. So I have a principle. I do not agree to change my mind just because you won the argument. And this I learned with Butler, because Butler can win any argument, even when he's wrong. Thank you.
Mike, thank you. We're going to try a little bit things different. I'll walk around with this microphone and try to get people so that we can hear the question. First, I'd like to actually make one small expansion to the story about the memory. It turns out that the max memory was designed with error correction. And I had put in a large number of registers and counters and logging hardware to find exactly the kinds of things that Bob's diagnostic subsequently found. It turns out, little to my knowledge, the programmers had never read those counters. So the max memory was sitting there making errors like mad, but they were being corrected. And when we found that out, then it was clear what was going on. And this caused us to make a terrible mistake in the design of the Alto. We only used parity rather than error correction. So you have to be very careful. Mutual suspicion, it's right. Questions?
If we left the parity out, we would have been way ahead.
Yeah, that's right. Well, that's what PCs do today. Questions?
Yeah, well, what's the relationship of the development of Ethernet at Parc and the Aloha system?
The Aloha, I've written extensively on this point because I've had 40 years to do so.
That's the thesis that was rejected also.
Analysis of the Aloha network was done, no, it was in the thesis that was accepted. So the problem that we needed to solve on the cable we had was how do you share the cable? And through an accident, I read Norm Abramson's Aloha Net paper, 1970 Fall Joint Computer Conference, which had this randomized retransmission approach to sharing. So I got Xerox to send me to Oahu for a month to study this with Norm, and then we implemented it in Ethernet, randomized retransmission. But we had lots of advantages. Well, Aloha Net wasn't a LAN, for example, and it ran at 4,800 bits per second, and it was, and the radio was this big, so we couldn't use radio. So we used randomized retransmissions, and the way we fixed it, there was a bug with it, which is it became unstable at very low utilizations. We had carrier sense and we had collision detection, and then we put binary exponential backoff, which causes you to not have the network go unstable. And that, by the way, that binary exponential backoff was microcode in the Alto, shifting a mask in 1 bit at a time with successive collisions and ANDing that against a random number to produce the randomized retransmission interval. Thank you.
And just to add to this, when DEC built their first Ethernet controller, there was a bug that caused all the random number generators and all the controllers on the network to get in sync.
How did the decision get made by Xerox and I guess also DEC and Intel to release Ethernet for public use and not try to make lots of money off a patent?
So I got DEC, Intel, and Xerox meeting in the spring of '79 because they could interconnect their products and Intel wanted to make a chip. And then during that time, there was a famous antitrust lawsuit going on against IBM. So suddenly the lawyers said, you 3 people can't be meeting anymore. So I called up my fraternity brother, who was a lawyer and who had been suing IBM, and said, what do we have to do to get this meeting? And he gave me a bunch of criteria. No marketing people in the room because they might fix prices. There must be a government observer, and you need a standards body. So we invented IEEE 802 to standardize it, and then we gave the specs to them. And in the atmosphere was the idea that we couldn't make a standard with something that was patented or had heavy royalties or taxes. So Xerox decided, oh, and that was your question, Xerox decided that to participate in making Ethernet a standard, it needed to license the patents for a nominal $1,000 charge, which my company promptly paid.
I'll finish off with this. Yeah, go ahead.
So I was always interested in the difference in the spec between experimental Ethernet, that is your Parc Ethernet, and the three-company product. And I think you sort of blended them together because the experimental Ethernet was not really that long and didn't maybe have that many stations. And I had the feeling that they stretched experimental Ethernet in length, in number of stations, and in bandwidth, and thereby somehow invalidated the prototype, and therefore it took a long time to commercialize. I wonder if you have comments on that.
None of that happened.
Well, actually, some of it did happen because there are some of us who looked at the spec. I had nothing to do with the specification process, but I looked at it, and at that time, Ethernet was competing with a 15 megabit per second token ring technology. And I pointed out that if they had gone away from Manchester coding to what's called MLT3 coding, they could be at 20 megabits per second without upping the bandwidth required of the cable. But nobody listened. It was cast in stone by that time. So Ethernet had to fight it out with
IBM Token Ring.
With the token ring.
General Motors Token Bus.
For the next 5 years, roughly, before it dominated completely.
10 versus 15. It was because the way I heard it, Ethernet arbitrates the use of the cable by detecting collisions between the packets. And the IBM salesman would go to the bankers and they would say, we know that you're planning to put in a LAN, that's right, and you're probably, the bankers would say, and the IBM salesman would say, you're probably looking at Ethernet and also a token ring, and the bankers would say yes. And then the IBM salesman would say, do you know that on the Ethernet, your packets with your precious dollars and cents in them are going to be colliding with other packets? You really want that. So if they just called it coordination instead of collision, it would have worked much better.
Back to the earlier question, the word collision came from the Aloha net.
Right.
Right.
So, and that was a big mistake. We should have called it a multi-access intersection signal or something.
Then we could make soup out of it. Okay, let's thank Bob and get a start on our.
So I feel for some of you in the audience, you're getting the Parc pastiche this morning, and you've got 2 more to go, and then lunch. And the afternoon promises to be more varied. I'm certainly looking forward to it. Like Dr. Metcalfe, I was not part of the BCC gaggle. Got recruited to Parc. I was coming back to graduate school at Stanford after serving in the public health service. You'll recall there was a war going on in Southeast Asia. And beyond the considerable charms of Parc, one of the reasons I joined was to learn from Butler and his friends, because I've always maintained, and I counsel graduate students, the thing to look for when you're looking for a job is people you can learn things from. And this was an unparalleled and probably never to be repeated crowd. And I had gotten to know Butler a little bit because when I was previously a student at Stanford, there had been discussions about this operating system that BBN was building for a PDP-10 equipped with a special paging box. This is what, of course, became 10X. There were a set of meetings called 10R. I don't remember what 10R stood for, but Butler was the chief entertainment at these meetings. He thought through all the problems. He knew exactly how to do the system. The BBN folks, well, they'd really never done it. They were having fun because they were writing all this wonderful code. But everybody else was a little wary. So we were having these kind of pre-user group meetings. And as I said, Butler was the entertainment. And of course, I'm actually surprised no one's mentioned this, but this became my introduction to the unit of delivery, speed of delivery of technical information that became known as the Lampson. Most of us could ourselves only achieve millilampsons. And Butler has slowed down a bit, I think, over time, but Fast, you know, did certainly capture it. Now, you'll recall Xerox made money back then by putting marks on paper. Computer Systems Lab, Computer Science Lab rather, was not founded to help Xerox with this business, nor to support its computer business. As somebody mentioned, Xerox had bought Scientific Data Systems, and you know, Butler and friends were complicit in helping make their computers better, but not as members of, once they joined Xerox. Many people in CSL thought that buying SDS was a mistake and thought that Xerox knew nothing about hardware or software, and probably a pretty good first approximation. But there were other pieces of Parc, as Chuck mentioned, that were engaged in Xerox's main business. And by the way, one of the reasons for those physicists, by the way, I'm also a failed physicist. One of the reasons for those physicists there is that a lot of them were solid state physicists worrying about selenium and how you use it as a photoreceptor, which, you know, a lot of the revenues of the company depended on. And we won't go into stories about making xerography work, but it is magic. But one of them, as Chuck mentioned, was the Optical Sciences Lab. And Gary Starkweather, who was a take-no-prisoners optics engineer who had worked in the research lab in Webster, New York, but was being marginalized because his ideas didn't fit in the mainstream of how copiers ought to be built, came to Parc, where he was working on ideas for scanning images onto photoreceptors. And as I think somebody mentioned, his scanner was affectionately known as a slot, a scanned laser output terminal. And Xerox, the Optical Sciences Lab hired Ron Ryder, another physicist who had actually never designed hardware, to build a character generator that would feed this gadget. Now, because of the way it worked, and we won't go into too many details, you needed 50 megabits per second burst rate to drive this gadget. That was fairly aggressive, 500 pixels per inch. So for this time, this was a tall order. Now, my understanding, and Butler should rise to the occasion and correct me here, is that Butler kibitzed on the design of this system. He wasn't a main designer, but the RCG, the Research Character Generator, as Bob Metcalfe introduced you to it, was a rack of about 2,000 Schottky TTL chips. That was fairly aggressively fast stuff at the time, run by a Nova mini computer. And correct me if I'm wrong, the first Ethernet connection to this gadget was actually an Ethernet interface in the Nova. Well, all right. Well, we could. At any rate, the copier was a Xerox 7000, a very robust machine that was nearing the end of its life. There were a bunch of surplus ones lying around, and so the Research Character Generator and the Xerox 7000 equipped with a scanner became, as Bob described to you, ears. So I'm really not competent to explain how this prototype, it was a research prototype, in the best sense of the word, got Xerox interested in computer printing. But somebody already mentioned that one of the big issues was that IBM was in the business. And the Xerox people thought any business that IBM was in was a good business. And it was also buttressed by the fact that Kodak, crosstown rival of Xerox, was beginning to get into this business with organic photoreceptors, which just scared the bejesus out of Xerox people because it was something they knew nothing about. So at any rate, Butler, I think, played a major role in errands to the ministers of state, as Gilbert and Sullivan would say, trying to persuade them what had to be done about computer printing, what was involved, and so on. Gary argued that the best way to get into this business was to use, there was something like 1,000 of these Xerox 7000 copiers in surplus. And he argued the best way to get into it was to just productize his scanner, productize RCG, and off you go. But Xerox at the time was developing copiers with roughly a 7-year development cycle. And they were working on a fancy new one called the Xerox 9200, which they called a duplicator. It actually had a selenium belt that was probably, 40 feet long, that carried sheets of paper on it and transferred. It was a big gadget. And so the Xerox management decided that this was the way we were going to get into the computer printing business. So it took a lot longer. It was faster. It was 2 pages a second. And it required re-engineering the character generator and, of course, doing a whole bunch of software that made this look like an IBM printing gadget, because that's what mainframe shops at the time needed. So I think Butler was probably a technical advisor to as this went on. We should ask him, but I can sort of imagine him in this role. He was probably very valuable for his quick assessment of design proposals and lightning attacks on stupid ideas, which I'm sure abounded. But he was also independent of all the other Xerox players, of which there were surely many, whether it was in the computer division or the copier division or the marketing people or what have you. But this business actually was successful, and as Chuck pointed out, you know, one of the few things that you can unambiguously point to that came out of CSL work, and Gary's and Parc generally, was the computer printing business at which they made a fair amount of money. Well, so that's the boring part of my talk. I want to now get to a slightly more interesting part. It's more interesting mostly because it's more interesting to me. I hope it's more interesting to you. So, but I wanted to show you a little bit about this first part because Butler was not above helping Xerox try to make money at its business. Even though he may not have approved the way they built computers and so on, he actually pitched in and did some heavy lifting. The other thing is, and I'm not sure, I'm maybe putting words or thoughts into his head, but it seemed to me he had an unusual fascination with pipelines. And the RCG was a pipeline design. And when I arrived at Parc, the summer before, a graduate student named Doug Clark had been asked by Butler, I think, to build another kind of display character generator. And when I arrived, Butler handed me this thing and said, can you make it work? Or it wasn't quite working. Well, it was another pipelined character generator, a very delicate design, very economical of chips and heavy on clever ideas. I don't think I ever really got it working. But I think if you look at many of the things Butler was involved in at Parc, it was pipelines. And as, you know, as the Dorado designer, I think of that as, in some sense, as his apex as pipeline designer. Well, so the part of the story I really want to tell you is how I got roped into doing a printer because it was Butler. I can still remember the meeting or where we were sitting. I have no idea what the topic was. But Butler, you know, would sometimes get this faraway look and start doodling on a piece of paper in front of the, and he'd kind of check out of the meeting. That's okay, we all knew something was going on. And it turns out, I think it was actually after the meeting, he took a bunch of us aside and pointed out that there was a way to take the stately Alto, to use Alan's term, which had only 20 megabits per second of total memory bandwidth, and somehow figure out how to generate video for a printer at roughly 13 megabits per second. Now, generally what you have to do to generate video, you have to clear the buffer, then you have to write in, you know, copy in character shapes, you know, turn on the bits that are going to be black, if you will, and then send it off to the printer. So the naive view, you multiply, you know, the output bandwidth by 3 if you want to figure out the total memory bandwidth you need to carry that out. But Butler's idea was very simple. It required a little bit of hardware. I'll tell you a little bit about it in a moment. But it mostly was a great system challenge. It definitely involved Alto microcode. It leveraged every piece of that economical design that Chuck sketched for you. Quasi real-time software. There was the ultimately server code and so forth to run a printer. And this is what led to the Dover printers. Gary re-engineered the slot, the exposure head. So I'm not sure whether Butler thought that I was the target of this lightning strike, but I was certainly an eager taker-upper because prior to coming to Parc, I had been doing computer graphics things. I knew this Alto software top to bottom because I had become maintainer of a bunch of things like the Alto operating system and had done my share of Alto microcoding. And actually, I should engage in a digression here because I notice other speakers have been trying to get you to laugh. I really like debugging. And the Alto world actually, as you've already noticed, provided many interesting bugs. Not because it was badly designed, but because it was, in this case, the story I'm about to tell you was fundamentally a controller of asynchronous I/O. And when you have asynchronous things going on, life can get interesting fairly fast. So the bugs, some of the bugs tended to be rare and very hard to reproduce or get reproduce in conditions you could attack them. So I would often, one of the reasons I got interested in microcode was changing, for example, disk microcode to inject errors much more frequently than the disk would, because that was the only way you could get the bugs out of the error recovery code. An idea which, by the way, I wish things like USB and so forth, various I/O bus designs had built into the standard. But the toughest bug I ever encountered in this way was a piece of operating system stuff that I inherited called BFS, and it did not stand for Butler's file system. It stood for the basic file system. So this was very rare. It was exacerbated by Ethernet activity, and the net effect was that there would be disk errors, that you'd read data from the disk and it would be wrong. So it turned out, I won't bore you with the details, it turned out to be caused by the reentrant error recovery code sharing a variable with the top level call. This was very hard to find, and it involved rewriting microcode and this and that. And it was even also hard to find because the code was devilishly clever. It had never been touched by anyone except the author. And yet here was someone who wasn't the author trying to figure it out. Well, you guessed it, it was Butler's bug. But I thought it was a bug worthy of Butler. And I certainly enjoyed it. So at any rate, Butler's printing idea was that all you really needed to build in hardware was some fairly small buffers, not a whole page buffer, say 16 scan lines. And then you would store the fonts in Alto memory. You'd use microcode to essentially copy those into the buffers that were in the hardware. The complicated shifting and masking was done in special hardware because the shifter in the basic Alto would shift one bit at a time under duress, or one position at a time under duress. So anyway, this was a great project, and there were a gazillion details to work out, but Butler, essentially in his sketch that sucked us all in, had, as I think Bob mentioned, he had foreseen the inner loop and what it was going to be and what had to be in the hardware and what could be in the Alto and so forth. So, but now I was going to say this at the end, but this was not an act of Tom Sawyering. So Tom, you recall, gave Huck the brush. So Butler doesn't do that. He keeps a brush as well. He also, rolls up his sleeves and gets his hands dirty. He's happy to enlist help from his merry band, but that doesn't mean he sits alongside and rests. So at any rate, I'm not going to go into all the details about how this worked. But there were other people involved. Severo Ornstein was one of the hardware designers that worked with me, and we had to generate fonts. Chuck mentioned that some of the graphics programs for the Alto were around fonts. Even when ears first started, fonts turned out to be a big challenge. And that was the time at which Knuth was doing fonts in a very different way, and there was more than a little contention about how it should be done. So I want to come to one last aspect about printing. So that was Butler with the sort of hardware-software printing system focus. But when I arrived at Parc, printing was done on a thing called an XGP, a Xerox, basically a giant fax machine, which was fed by a serial stream, a video stream generated by a special card in the Nova. And Peter Deutsch was the beleaguered author of a piece of software that would take text files with embedded codes to change fonts and things and print them out on the XGP. And the reason I say he was beleaguered is because people just hounded him for features in his code. Every time somebody wanted to generate a document that looked a little different, the footers were formatted differently, or the page, whatever, they would try to beat up on Peter. And Peter fought back, as he should, but ultimately acquiesced in a number of things. So William Newman and I actually proposed a different approach, was to take more the attitude of a graphics display and a geometry problem and specify, if you will, geometrically where things should lie on a two-dimensional coordinate system. And characters were then just little images in that coordinate system. And so we built a file format called Press, which took this approach, and then built a bunch of software that would create full-page images and send them to printers slowly. These were images we buffered on a disk, the disk that was faster than the slot scanner. We couldn't do that for Dover because the disks weren't fast enough. and we couldn't generate the pages fast enough. But press nevertheless became really the sort of the workhorse of printing. By the way, Dover could not print a full-page arbitrary bitmap. Nope. There were other printers that could, but not Dover. So, and there was actually an interesting story. I was flabbergasted. I had put together a little proposal about this and was talking to about press and was talking to a senior research manager, not Mr. Taylor, at Parc. And I was driving in the break room what I was up to, and he was asking, being very managerly and trying to find out what his youngster was doing, and I explained all this to him. And I had thought that the idea of research in computer systems was to set some objectives that were, hard but doable. You could kind of see how to get it done, and somewhat risky, and learn by building the system and measuring the results. But this guy actually said, it won't work. And I was astonished. Luckily, I didn't pay any attention. This obviously was not the man sitting here in front. But it was an illustration of one of the reasons why it was important to have him around to counteract some of this. But at any rate, as Xerox became more interested in the computer printing business, press clearly wasn't going to work as the final thing. And we started working on a thing called Interpress, and Butler was the language designer. And one of the key things, again, I won't go into details, but one of the key things that he realized is you really wanted a scheme, it wanted to be a language, something that you could compute with to decide what to display, especially to handle repeating patterns and so on. But you wanted each page to be able to be independent from each other page. In other words, to be able to render page without a side effect that would cause effects further down the document. Because you might have to print them out of order. For example, some of the printers you preferred to print in reverse order so they stacked correctly. Or you might have to reprint certain pages after a jam or what have you. Well, Interpress got to be very complicated and was never really the main page description language for Xerox or Xerox printing. But instead, what happened is John Warnock, who had been working at Parc at the time and had come from Evans and Sutherland, where he had a little language for generating geometry for flight simulator geometries, adapted that to an imaging model similar to presses, and that's what became PostScript. And he and Chuck Geschke went off and formed Adobe and made a great success out of it. But I do wish to point out that among other things that happened to PostScript is they came a cropper on the page independence problem. First of all, you may recall there were what they called formatting conventions or something, some ways to use the file to essentially make annotations in it that said, here's where the page breaks are, and this page doesn't depend on anything that came before. And then when PDF happened, again, they recognized that you needed to be able to make each page able to be independent of all other pages. So this was an example where Butler was prescient and tried really hard on an important problem, but I think Interpress probably failed partly because it wasn't really Xerox's business to be specifying that sort of thing, and secondly, it was probably had a mild case or maybe an extreme case of second system effect. So I've tried to illustrate a few things about Butler and how he operated in the lab. His inspiration is always accompanied by a twinkle in the eye. You'll see the twinkle right now, as a matter of fact, as he's sitting over there smiling, and usually a laugh. We all recognize that laugh. He's versatile and skilled beyond anyone I know or have ever had the luxury of working with. But I really think his key benefit to me and to many of the things that you've heard about is to ferret out really key ideas or principles that are the crux of solving a problem, and then propelling the rest of us to work on them because it's so exciting. Thank you.
We have a mic, and we have time for a few questions. There must be questions.
No, it's not a question, it's a comment.
Oh.
Okay, you talked about Interpress failing because of technical reasons. but I have a totally different memory. Sitting there listening to Jerry Elkind, I believe it was, telling me that in business, this couldn't possibly work. If Xerox made Interpress a public standard, we would be out of business tomorrow. And and they beat us up over that subject, and Geschke and Warnock walked away.
Right. I think you're describing something that happened after I left. So thank you for adding that.
Let's see. There were some questions back here. Alan.
Now it's a non-question, because I was going to ask you if you cared to relate what happened to that executive, but now I will not ask that question.
It was somebody, Cynthia, you had a question?
Can you say anything more about the font wars?
About
the font wars?
Font wars.
Font wars.
Well, so I'll say a little bit, which is and just speaking for myself, my objective was not to solve the font problem. It was to enable work on printing. And so the fonts we dealt with were pretty crufty. And there were all kinds of errors, and we were total neophytes and did not take the time to really do it right. And in fact, to this day, I can remember bicycling along sidewalks in Palo Alto, and you'd see 8.5 by 11 sheets up, advertising a yard sale or something, and I'd say, I know what printed that. That's a Dover, because the lowercase Helvetica R bold has a spacing error. And there were errors like this just everywhere. Don was much more methodical about what he was after, but he also had, a very specific take on things. Now, needless to say, where we are today is outlines are what work, because it's a more general framework and more easily, I think, manipulated by designers. But it's also has a much bigger investment in scan conversion software than we made. We did the obvious, simple thing to get on with it. Part of it is we were interested only in xerography, which is just binary, no grayscale. And we had xerographic printers that were, how can I put this delicately, distorted the image as they copied. You may recall that if you took a thick line and copied it on earlier copiers, it became thinner. Well, so we weren't trying, we did a little bit to compensate for that, but we didn't have a robust enough imaging system in most cases to be able to really see the benefits of high quality font work.
Dave?
It's always inspirational to hear about all the skating near the edge that Parc did, where you're actually making amazing use of hardware resources, just a little bit of hardware and a lot of cleverness. Were there examples where you skated off the edge and where things actually didn't work as you intended? Because I think we've heard a lot of success stories. I've never really heard of a story where things actually didn't work.
Well, the memory story was an example of skating off the edge. Skating, in that case, sorry? Signet was another example of skating over the edge. Signet was actually a much more reasonable design if you were an electronics guy. But it was a.
You said it was basically it's what Cisco
does today.
Does today.
Yeah, it's you have those little network switches. That was Signet. Any more? Okay. Well, I will introduce our final speaker of this session, and I have to tell you a little story about Alan. The last time I was in a venue where Alan gave a talk, he was challenged to give a 30-minute talk, and after the talk finished, I said to him, Alan, you went a little overtime. And he said, how long did I take? And I said, 90 minutes. So the reason that Alan's talk is at the end is so that we will be running into lunch. So he might be a little easier to stop. I also have some of that physical stuff I was talking about if that doesn't work.
That is definitely the most.
The way Alan got away with his 90 minutes was that he had some very polite German hosts who were extremely unwilling to interrupt a Turing Award winner in full flight.
To be fair, he had a lot of interesting stuff to say, too.
There are two things to point out about that talk. Since you've ruined my first point.
my first point was Chuck Thacker says that I'm biologically wired for giving talks longer than an hour. However, we can sometimes resist biology. However, just to show you how things actually go rhetorically, I went back and looked at the video of that talk. And my talk was actually just an hour and 5 minutes. And the other 25 minutes that crept into Chuck's estimate were quite generated by the audience, which I had no control over. Okay. And actually, I decided to, I have an urge to explain things, so I decided that if I trap myself in trying to say something of substance here, that we would have this biological phenomenon. So I'll just point out that Thornton Wilder said in a play called The Skin of Our Teeth, in there was an old fortune teller, and the fortune teller has a great line where she says, the future is easy to tell. Nothing easier, but who can tell the past? And the reason it's hard to tell the past is because if you were there, there are all these details. And most of those details are actually critical for the memories of people who are back there. That's why it's so easy to digress on this stuff, because it was a lot of the things that were important and vivid were actually rather small compared to coming up with a vision for improving computing in the future, which is what we started. We started out not worrying so much about the past, and so the aim at Parc, which I think of as the shared aim of the ARPA community that many of us came from, was a relatively simple one. It's just that nobody knew how to do it. It had been gestured at. Now, the title of my talk comes from one of the early encounters with Butler, who I'd met a few years earlier, but I think it was in '69. And in those days, there was a kind of a traveling circus of ARPANET meetings that were run by John Postal. And Utah was going to be the 4th place on the ARPANET. And so one of those meetings was, you weren't there, because who could forget? Even then. But Butler was invited for this, and he had a slot in the afternoon to give an hour talk. And as things happened, the meeting dragged on and dragged on and dragged on, and it was almost the end of the day. And finally, it was time for Butler to give his talk. And he got up and looked at his watch, and he said, I've got a plane to catch. And he proceeded to give us the talk in 20 minutes without actually leaving anything out. And I believe that was his main heuristic back then for trimming things, which was instead of going through all the effort you have to do to choose what to leave out, he simply left everything in and sped up. And this particular talk was on Cal TSS. And what's really fun if you like Butlerology is you can find essentially this talk in Butler's page of the many papers he wrote, written up as a paper for Infotech, right? Yeah, Infotech reports. And what's interesting, I have a vivid memory of this talk. By the way, the talk was completely understandable. It was absolutely as clear as a bell. And if you read that paper, you'll see that talk. Pretty much every detail in there, and it was about a relatively new way for most of the people in the room, people who had not looked at, for instance, the B5000 or some other schemes for doing protection. So there's a lot of detail and how you confine things and how you can get to things without being allowed access to them and so forth. So it was a beautiful, intricate scheme. And at the end of this talk, a fellow graduate student with me, Steve Carr, who actually had been with Butler at Berkeley and came to Utah with Dave Evans, Steve Carr turned to me and said, you know, it's just a privilege to know somebody like Butler. And pretty much everybody agreed, and still do, Butler. It's just a privilege. And that's what I want to give a talk about that today, because it's a way of getting out of the fun technical details. But I thought it'd be, especially since I operated in what I thought of as the magnetic field generated by ARPA, and for many years at Xerox Parc was operated in the magnetic field generated by Butler and Chuck and CSL. But I actually wasn't part of that group except spiritually. I had a separate group. And so I want to give you the point of view of somebody who worked as a kind of a colleague, or thought of the dominant group at Parc as colleagues. So I think the simplest thing is that in the old days when people were trying to figure out what does it mean to be a computer scientist, these days it is not even worthwhile asking that question, because if you go to any university, they'll tell you computer science is what we teach. And that's a far cry from back in the 60s when it was viewed as an aspiration, like software engineering, which is you get a similar answer from. Both of those have certain oxymoronic qualities to them if you compare software engineering with what I think of as real engineering, and if you compare computer science with what I think of as science rather than library science. If you try and take those two operative words seriously, I think we're at our best if we still think of those as aspirations today rather than a fait accompli. So we don't ask this question. But in the old days when people ask, well, what is a computer science? I say, well, Butler is one. I don't know what being a computer science is, but whatever it is, he's one. And my first brush with Butler was through Dave Evans, who had been at Berkeley, who came to Utah to start an ARPA project. And Dave brought with him a couple of Model 33 teletypes, which were hooked to Engelbart's SDS 940. And the SDS 940 was kind of a commercial version of the Project Genie machine that a number of people worked on in the mid-60s. And from my standpoint, it was the first time I'd had a chance to do anything like interactive computing. I had been a supercomputer programmer before that and actually worked on the big brother of the 6400. I thought of the 6400 as not being that much of a machine because it really wasn't all that parallel compared to the 6600, which was, we thought of as about a 6-pack of beer per instruction if you really wanted to make it run fast and not miss any memory cycles. So I never really had much contact. And so my first contact with interactive computing was Cal. Butler will remember Cal. So Cal was a practical version of the first really good language ever done for end users, which is called JOS at RAND. And what was interesting about Cal was you could do robust programming on it because Butler had done a line-by-line compiler for it, right? And there was, basically each line was actually kind of linked to, and you debugged, so you could put breakpoints and stuff in there. And so the beauty of this system was that you could do quite serious computations interactively. I started in '66, and this was a revelation to me. And it started a path. And of course, there was the Cal manual. And then, of course, the manuals for the SDS 940. And Steve Carr explained to me that they didn't have any documentation for the Project Genie machine. And somebody asked Butler if he could take dictation, do dictation. And he said, I don't know. And you can correct this story if you want, but it's a great story the way I tell it. And they put Butler in a room. They put Butler in a room with a microphone, and he just dictated those damn manuals, including Steve Carr said where the pictures should go on the page. So those were legends I heard about Butler before I ever met him. But I felt I'd been well introduced to him by seeing the system that he'd done. And then, of course, there was the Project Genie OS, which I started delving into. And there were a couple, Engelbart had started to use it it was the system on which the grand demo was actually done. And the thing that struck me about the Project Genie OS, this SDS940 OS, was there are 2 or 3 things in there, besides what you expect an operating system to do, that were really striking to me. And again, Butler can correct me, but the way I looked at it is, wow, this machine is designed with failure in mind. It's essentially designed to fail. And all the other systems were designed as though they're going to work perfectly. And so when the time-sharing system crashed, it would take forever to get the thing back going again, whereas the 940 would often come up in just a couple of minutes. And part of this was because the operating system used some of the computing power and time, even in that machine was a 24-bit machine, about a half MEP, running multiple users. It's hard to even imagine running multiple users on something like that. But it was a marvel of compaction in many, many ways. And that operating system basically tried to write out pages, whether it needed to or not. If a page was dirty, it wouldn't wait until somebody needed new storage. It was constantly cleaning up. And this had 2 fantastic benefits. One was the chance that there was room enough when you had to bring something in was very high. You do not have to swap out to swap in. The other thing is an enormous number of pages were essentially checkpointed on the disk. And so when a crash happened, it was much easier to recover things. And we later used those ideas in the very odd object swapping system we did for Smalltalk on the Alto. Because the Alto, Chuck knows, is my favorite machine. But a simple way of looking at the Alto is about once a day, for no apparent reason, it would just crash. And it was just an idiosyncrasy of it. And at some point, we decided, and the way Bravo dealt with this was something really good, which is a replay file that really worked. And it was the #1 reason that Bravo got users was they guaranteed 2 things. We'll print if the printer is running, and if you get a crash, we can bring you up to within a couple of characters of where you were. And they were able to develop this software with live users through many, many different things because they had done these 2 things essentially. You didn't mention this, but I think that was just fantastic. So you got a lot of user feedback early on and all through the process. And the other thing that was kind of amusing about the 940 is that Butler decided that programmers were not responsible beings. And of course, that was known to be true even then. And so the 940 was set up to train programmers, actually to punish them if they weren't good. Am I wrong yet? Because remember, well, on that machine, you basically were given the opportunity to predict what your working set was going to be. And if you were right, then you would be run on the fast queue. And if you were wrong, then you were run on a slower queue. I remember that vividly. And it worked like gangbusters because programmers all of a sudden took, because you can only get 8 pages at a time in on that system. And because he limited it to 8 pages, you could line up 4 users in a 64K machine. And so the amount of efficiency that was going on without stochastic events was fantastic. Okay. So I wanted to say something about magic people. To me, a magic person is somebody where it is hard to see how they can do it. So we know great people, great person is somebody where we can see what they're doing, we can understand what they're doing, and it's incredible. So the first magic person I ever encountered was Ivan Sutherland. It was just very hard to see, on the one hand, where he got his ideas from, and on the other hand, how he could pull them off. And I think of computer science as being this odd thing that is partly theory. Most of the interesting things get done have something more than an ad hoc model. And they really don't count unless they get implemented. And so these magic people are people who can come up with a theory that is unusual, seems to have leverage, promises a new world. And then somehow they're able to do what Michelangelo could do, which is to get up on his back and paint the Sistine Chapel for 4 years. So that's a magic person. Butler is a magic person. The range of stuff you have been getting an idea of that he was willing to tackle, things that he was willing to learn on the fly and so forth, I don't think is matched by anybody else I know. So I want to say a little bit about making progress, and I don't have to mention Taylor because you're going to talk about Taylor tonight, are you? Okay. So I guess I should say one thing about Taylor is kind of a magic person also. And he was magic in a sphere that we technical people are often not so good at. He was the most amazing combination of being able to understand and deal at the visionary level, and also understood the psychology of people who are actually rather unlike him. And he had a feeling for what synergy is all about. And I'd like to just say a few words about process here, because in the accounts of Xerox Parc, the things that are weakest in the ones that I've read are, for instance, why was the ARPA community so successful at doing things? Why was the Parc community so successful? And it had to do with what Jennifer said better than I could, which is everybody was uncompromising, and somehow we were able to work together at the same time. And I still don't know exactly how that worked, but it actually did work because my group was, I think, affectionately called the lunatic fringe. I've never checked into the affection part, but that's what Taylor used to call us. And if you think about what Parc was into, you can imagine what we tried to do. So it was a little bit different. And however, we loved the living lab idea, which I ascribed to Butler early on. I remember him saying, let's not do any more bubblegum together demos. Let us try to engineer our inventions so that they can be used by a wide variety of people. That will put some reality into it. And we all fought him for a while on this, but it turned out to be one of the best things that we ever agreed to, because that extra engineering injected early into the process often saved a year or more on many of the projects there. And I learned something from that I didn't really. Yes, have you got your laser pointer ready? Okay. Well, it's going to take more than that, Chuck. Okay, so I'll wind this up by just pointing out a couple of examples of what I call parsing Butler. So the most important thing for anybody to realize about Butler, and I think people do today, but when Butler would go, this will never work, it wasn't like the other executive. But because when Butler said that, it didn't mean stop. just meant take care. When Butler said, this is glacial, didn't mean stop. Meant find ways to speed it up. When he said, this is majestic, that was our improvement in small talk. First it was glacial, and we got it up to majestic. And that didn't mean it was fast enough. So I'd say that the Metcalfe's principle here, one of many they've articulated, but the one at the end, which is the most worthwhile thing, was to be able to argue with Butler whether you won or lost. I will confess that I never won an argument the same day with Butler. It was just impossible. But what was cool was he would let me come back a couple of weeks later after I'd thought it through a lot more, and he would let me win those arguments. And so I'd like to say that from the standpoint of that time, what is most memorable to me now is not the technical stuff that we did. What was really cool was to enjoy the kind of symmetry that comes from this uncompromising approach. Because uncompromising doesn't even mean you're disagreeing. It's just saying this point of view is hugely important. And what happened was that people tended to look at each other's point of view even through these lenses. And in the end, I think we all wound up using each other's ideas in the most powerful way I've ever experienced. Thank you.
Well, I have done another impossible thing. And that there are now time for questions before lunch.
I knew there would be. Exactly.
Oh, yeah.
Exactly. And
okay. In the back. You're going to have to, well, I'll come
But the real
behind.
question is, did you like the talk in Germany or not?
Yeah, it was actually quite
well,
good talk.
Okay. So who cares
That's why
how
nobody
long
was,
it was?
willing to stop him.
Hi, I'm a colleague of Butler's. My name's Mary Gray. And my question is actually to Butler to hear how he responds to him being framed as Magic Man. And specifically, I've seen this magic in action. I'm just wondering what he feels has given him the capacity to have the breadth of engagement that he does, because it's really humbling to argue with Butler. So just some insight into how to better beat him at his own tricks.
It's not humbling, it's a privilege.
I have to say, I don't get this magic stuff. My view is I'm just following my nose.
Yeah. I could have even guessed that. And, Ivan Sutherland doesn't see it that way. None of these people who are amazing on the outside have any sense of that. That is exactly what they're doing. Is they're just seeing a little bit. It's like driving at night with really powerful lights. They can see further ahead, and I think they also have an amazing way of producing the synergies necessary to get the practical vetting of the ideas.
Although it's also true that I don't think there's anybody in this room who's ever won an argument with Butler on the first day, with the possible exception of Lois. More questions. Don't be shy. Bob.
Similar was the Alto to the Dynabook?
Well, the original term we had for it was the interim Dynabook. And I think Taylor, both for branding reasons, decided to call it the Alto, but it was also good to have a single name for it, I think, because the interim Dynabook didn't. The Alto was meaningless, but so was the interim Dynabook unless you're there. And to me, what it was on that level of personal computing was another motivation for the shape of the screen, because that was the kind of the shape that the Dynabook was. And the idea is, by spending a lot of money now, we can get the future 15 years ahead now, because the software is going to be the gating thing on this. And so I think we only made a first pass on personal computing, and probably the most disappointing, two disappointing things about personal computing was that people haven't done much of a pass on it since. But I think the other thing is that the commercialization has tended to follow marketing lines, and marketing people hate learning curves. So they basically have not put any effort into getting the users to be more savvy, and so the users are spending about 95% of their time just using imitations of old media for convenience. And that wasn't the computer revolution any of us had in mind, but that's kind of where we are.
It's also certainly the case that we have not done a good job in providing our users and our customers with a good conceptual model of what they're doing.
Yeah.
This is in my view, a very big flaw of our industry.
Yeah, I mean, granted, it's incredibly difficult. And if you look at the user pool in the 80s when PCs came in, really no part of the user pool, except possibly for beginning university students, was well set up for what was available, because business has always been curious about computers. And so they weren't a good target for trying to really augment what they were doing. And I don't think consumers were a good target. And the systems just weren't quite ready to put into schools as we'd envisioned. So I think the gating decade for many, many things, even that the Intel and Motorola processors were too slow to do dynamic languages, wow, that was really a problem. And
I think what you say is actually a little bit misleading, because the business users in the 80s who were paying the bills, because the machines were expensive, they actually had a very clear conceptual model. It was called the spreadsheet. And they understood it very well, and it fit their needs extraordinarily well. The fact that you don't find it very interesting is that's certainly true, but you're missing an important part of the whole story.
No, I don't think so, because no, actually,
I'll remind Alan of the fact
actually,
that he's never won an argument with Butler on the first day.
I know, and doesn't mean I'm going to shut up.
Need more questions.
Now, just read my 1984 Scientific American article for what spreadsheets should have become.
Charles.
Thanks. As you know, I like extreme and outrageous statements, and I remember at the time I was very inspired by your remarks about Kleenex. Would you care to repeat it and also comment on how you feel about it now?
Well, there were a couple of different contexts for this. Part of it was worrying about whether we could get the next thing that was like an Alto, because the Altos wore out as far as providing leverage every 3 years or so. So the question was whether we were going to was Xerox going to pay for the next round of stuff? And the other thing just had to do with people's worries about what we were spending money on the Alto.
What did you say about it?
So what I said is, I said computers are just like Kleenex. You use up the box and throw it away. You know, that's just reflecting Moore's law, but it's also saying, hey, don't use 60s worries about memory size to preclude thinking about a bitmap display. That was a big controversial deal. We used half the memory on the Alto for a bitmap display, and the Alto only had 128K bytes. So we're using half of it just to put this thing up that you could put any picture on. But the other thing was the computing power. And the way I looked at the Alto was, what was delightful about it is there were a lot of things you did not have to optimize to try out. So we'd go out and drink a couple of pitchers of beer at the Black Forest and come back and just try out user interface ideas all afternoon, and we wouldn't even save our code.
Kleenex has actually happened. Because, for instance, the battery is sealed into my phone. I have to throw it away.
Yes, well,
One more question right here, too.
Okay.
I just had a bit of a left field question for you. It was a fantastic talk, but I'm thinking about the other side of your life as a jazz guitarist and as an organ player. I'm hearing these fantastic stories of people who were so driven and so individual, almost like soloists, yet you had this capacity to work together and to produce these things in a very kind of resource-limited kind of way. Could you talk a bit about that process as improvisation? Was there kind of a sort of an improvisational model, and how did these people, these soloists, sort of work together in these kinds of very harmonic ways?
You know, of course, there is some of that, but I think for a musician, the two processes that could hardly be more different are composing and improvising, because you have completely different constraints. You have real-time constraints on improvising, and you don't have time. And compared to, you know, this thinking fast model, which I think is somewhat unfair, Bob, but it was a fun part of your talk. So what characterized my approach, my group's approach, is we were slow. We did the slowest systems that got successfully done at Parc, because our ideas were all about integration, all about user interface, all about modelessness. And in order to do this, we had to run interpreters. We had to do we did a different system every 2 years. And so one way to look at what we were doing by the end of the 70s is that we had the very thing that Butler was inveigling against. Is we had something that was great for making new versions of itself. And we had examples of what the world was going to be like in this integrated environment. But it wasn't, I wrote every paper I wrote on Bravo, because Bravo was real, and what we were doing was showing a framework for what was going to be possible in another 10 years or so. So it's just a completely different. So to me, and the reason, you know, it's hard to have a certain amount of emotion about this, because to me the big deal at Parc was that we were a fringe group, and in many worlds where the people have the resources, and they were sparse resources back then, they would try and get out the unorthodox, and it was absolutely not the case there. Butler and Chuck helped us many, many times, even though what we were doing was against when they had to explain to Xerox what they were doing, what we were doing was actually somewhat different. And it didn't matter. That's the key of this talk. The key of this talk is, just as in biology, the number one deal in biology, as Lois can tell you, is biology generates variety. And it's the generation of variety that allows new things to happen. And that was not sacrificed in any way at Xerox Parc, even though people had completely different time horizons and so forth. That's why it was great.
The other thing Lois likes to say is every molecule does more than one thing.
Yeah.
That's definitely was also true of the people at Parc.
Yeah. So some of the people at Parc were like physicists, and actually were physicists. My background was in biology. So what I was interested in, the more squishy aspect of systems. So when I looked at systems, I looked at my analogies, like when I looked at the Cal TSS and the B5000 stuff, what I saw were things that were trying to become more like biological cells, which is not generally the way I would describe the people who were designing them. They had other ways of looking at them. But it was a toleration of many different kinds of system views that led to the richness there.
We can probably take one more question.
Yes, sir.
Yeah.
Is an iPad a Dynabook?
No.
Would you care to identify yourself, sir? Okay, with that somewhat irrelevant observation, we'll
No,
we'll break for lunch. Thank you.
Thank you.
Let me give the